So we're going to get started. We are looking today to see if we can finish up chapter 3 of 33 examples, which focuses on universal constructions. And we've been talking about a variety of universal constructions over the past several sessions. These include things as basic as terminal and initial objects, or as important as them. Turns out all universal constructions, as I understand it, can be viewed as initial or terminal objects in some category. We've talked about co-equalizers and equalizers last time. Before that, we talked about products and co-products. And today we're going to be, and all of those actually play an important role in our path forward with sheaves. There's a really valuable equalizer perspective, for example, on sheaves. Limits play an important role in understanding sheaves. But today we're going to talk about two final ones that also are really practical. They're important in the sheaf context, very important for sheaves and co-sheaves, respectively, for pullbacks and pushouts. And finally, that they also play a really important role in our growing categorical frameworks and for the efforts to which we're contributing. So in things like algebraic ABMs, and in things like stockflow.jl, pullbacks and pushouts are key categorical gadgets that of which we make use. So I want to talk about these, and to do that, I'm going to probably do a little bit more screen sharing today than I'm used to, but during office hours we can make use of the board. So Eugenia Cheng comments on pullbacks and pushouts that they're more advanced universal properties, showing more of the general features we're missing from the special cases like products and co-products we've seen so far. And if anyone's interested in diving more closely into them at a manner that is rigorous and intuitive, I'd recommend chapter 19 of her book as expanding on these. I'd also recommend these videos, which are really quite excellent. Okay, so I'd like to start with pullbacks. Pullbacks are generalizations of products. And I want to, though, step back a moment to motivate them in a bit of a more general context, because otherwise it can seem to be maybe coming a bit out of left field. It turns out three of our universal constructions are what are called limits over diagrams. In Sheaf Theory, for example, chapter 3, this is actually discussed some. Terminal objects, products, and today pullbacks are limits of our diagram. So I'll talk about that, but you may recall the idea with the diagram is we have a small indexing category, a small shape category, with morphisms and objects, and we don't get into that category, all the details of what objects represent or anything. No, or what they constitute. No, we're just treating us as shape. And you remember that a limit is a morphism. It makes use of a morphism from that shape into some other category. But there's also a constant mapping which forms a cone, and we'll talk about this. And we take a limit over a cone with this specific shape category, picking out certain morphisms, the certain subpiece of the category into which we're mapping, over which to take this limit with a cone. Now, I should note that these constructions are limits over diagram, and their duals are co-limits over diagram. So initial objects, co-products, and pushouts are all elements. I should finally note there are some universal constructions, as I understand it, such as exponentials, which are really useful and valuable and practical, but which are not limits or colimits. Okay, so let's talk about this idea of a diagram and where it factors in. So so each of these constructions, products, pullbacks, terminal objects, have a diagram associated with them. And that diagram, by mapping it into some other category, well, it is a mapping. A diagram is a mapping from a shaped category into a category. And it picks out something. So a diagram which has just dots like this, if it's mapped into a category, it will pick out two objects, a pair of objects, right? One for this one for that one. Possibly the same object, right? You could pick out the same object twice, yeah. And what we're going to be doing, you may recall for products, but this generalizes for limits, is we formed a cone over it. And again, there's a construction involving a constant functor, which maps over to form this. And we have this cone formed where there's needs to be a morphism down in this target category from this vertex object, this apex object, I should call it. So apex object down into each piece here, such that this matches some universal property, right? That this is the best such cone, right? This cone is such that any other competing cone that has these morphisms down to these two objects, I'm talking for product here, these morphisms down in our category, there's a unique morphism in our category from this contender, this pretender, to our product object or limit here. Such that, and this is extraordinarily important and it will be followed through, these triangles commute. These have to commute. In other words, this mapping has to be the same as the composition of these mappings. This mapping has to be the same as the composition of these mappings. In other words, if we had an X, projecting it down, getting this object, having that morphism, we can get that morphism by mapping it into our universal, our one-stop shop, our sort of quintessential product or essential product, and then mapping that down. We can get all the functionality we need from this one as far as mapping these things down through this one, through a unique mapping to it, right? We can take our fancier one with a lot of extra cruft, maybe this is a triple, and with some extra things stuck on in essentially, and we can map it down to our product, which gives the real goodies for mapping down to this, mapping down to this. This is some inessential cruft. This is the best one. This is the quintessential one. This is the essence of what it means to keep information about these two objects. Are we okay with this idea? This is for product. Now, the idea of a limit is going to generalize this. And watch this. So here we had a diagram with no morphisms picked out. So in other words, our shape category, all it had were these two objects. It didn't have any morphisms in the shape category. So when we mapped it into the target category and we consider building a cone over it and the commuting conditions, we didn't have to consider any morphisms down here. They weren't picked out by the diagram. We're taking limits here in the context of what's picked out. By contrast, here we're getting this diagram picking things out. I do want to emphasize here that the diagram, when we mapped it over, it picked out two objects in this category. It actually didn't directly, that diagram, when we mapped it over, didn't directly pick out that mapping of the diagram into the category, picked out these two objects. It didn't pick out V. V is picked out with this constant functor, which is a separate functor. Here, and so these morphisms aren't picked up by the diagram itself. but they are the morphisms in our category into which we have mapped this and into which we have the constant. Okay. But here, with diagrams in general, or with limits in general, we're going to have a diagram that can have morphisms in it, like this one here. This is some diagram. We could map it into our target category. Remember, our diagram's a functor from our shape category. This is our shape. And map it into our target category. Okay. Yeah, that's nice. So that's just what we get. And then we have this, again, we have this cone that was picked out as this other functor with this apex. And these are morphisms in our target category. They've got to be there. They're not necessarily these ones, although they could be, but there are others in this, there are some in this category. And the point here with the limit is that all these triangles have to be commuting. Like this has to commute. So if I go this way and this way, it has to be the same as this way. If I go this way and this way, it has to be the same as going here. If I go this way and this way, it has to be the same as that. Okay. But the limit is, again, has this universal property associated with it. It's the best. It's the best cone. It's the best cone over it, right? It's the cone for which every other contender cone factorizes through it in terms of how it relates to all these objects. And remember, it may not exist for, a given limit may not exist, but there's this broad set of categories for which all limits exist, called Cartesian categories. And set is an example of a Cartesian category. Set would take the limit of any height, of any product of any pair of objects. We could take limits of these diagrams. It's very pleasing. And there are also categories where maybe you can't take the product of any two pairs of objects, but there are products of some objects. That's useful. It's a useful thing. All right, so this is our useful category, a universal property. And this is for our limit. So we have a general diagram. A product was special because we didn't have any morphisms here. It was a particularly simple case. In general, for limits, we're going to have these morphisms that we consider from our diagram. Okay, that's what I wanted to orient you to. And indeed, this is going to be the case for our pullback. Okay. So this is from David Spivak. David Spivak was showing in this course on polynomial functors that we took, like, like a pair of objects. This is like the product pair of two things, right? Pair of two objects, right? And this is one morphism from this shape category. This is the diagram there. And this is the diagram here from a single object, just picks out an object. From an empty category, there's a unique mapping here, right? And unique, hence the exclamation point. Pullback is going to be this one here. We have a diagram of this shape, this here shape. Okay. And it turns out equalizer was one of these diagrams. I didn't emphasize it last time, but the equalizer is also a diagram with these two objects and two arrows between them. These are all examples of these limits. Okay, so this is our diagram here. Are we comfortable with that? Okay. Now, so we're going to be considering a limit over it. So all these triangles have to commute, right? If you go from V to A and then to C, that has to be the same morphism, right? If you go from V to B and then to C, that has to be the same as this morphism. And it follows that, so these have to be the same. Now, because this commutes, we commonly don't draw this. This is implied. We know it's there and we know what it is. It's the composition of this one and this one. It's also the composition of this one and this one. They have to be the same. So we don't even draw this, just like we omit identity arrows or omit composition. This is totally given it's given as the composition of this and this and the composition of this and this. So we don't even draw it in our pullback. So this is what it looks like. This is our pullback, and it's a pullback square. Now, the pullback is not only distinguished by, having this object with our diagram like this, with these morphisms, that's such that things commute. It's the best one, the quintessential one, right? The essential one, the most minimal, sort of best, most efficient one. So it's the one V, such that for any pretender, any contender for its throne, that also satisfies these properties about commuting triangles and so on. There's a unique morphism for this to this. So this is maybe something that is like this, but has some extra cruft, some extra inessential stuff. And we have a unique way of turning that into our best one, our most essential one, the one that captures the essential properties in the most efficient way, such that, all the factors commute. Okay? So just remember, we're kind of omitting this diagram, this arrow here. That's this arrow, right? V to C. We're omitting it. It's there, and it's because this commutes. It's this, and it must be also this. It's a single morphism that at once is this the composition of these two and of these two. So we're just remember it's there, and it's totally defined, and this is a commuting square reflecting. Are we okay with this? Okay. So and if you were to draw it out, you'd realize, oh yeah, once again, these things commute. The triangles commute if you were to draw. Okay, so this is our pullback square. I'd like you to note it. Okay, I'd like you to note the pullback is in the upper. What we call informally the pullback object is in the upper left. Just recognize that I put pullback in the quotes because it's really this whole structure. But we call this often the pullback. This is the pullback of these of A and B over C, fibered over C. Okay. Okay. So now, like with all these things, there's this beautiful intuition. It's easy to be overwhelmed by this at first. To just stare at it. Grothendieck, the foremost figure, arguably in category theory, Alexander Grothendieck. John Baez tells me the story that Grothendieck at one point was staring at these diagrams and saying, like, what am I missing? Like I'm not getting the point. So he too, there was a time where he too wasn't grokking it at first. Everyone has to develop these skills. But I will tell you, if it's any motivation, if it gives you motivation, that there's tremendous intuition that comes with this after a while. And that if you play around with it enough, try some examples, etc., and actually apply it in practice, you realize that, oh, yeah, it just makes a world of sense. There's just all this intuition. So I'm going to try to convey a little bit of that intuition in as much as I've come to. Okay, so one thing is that people will talk about, and you'll hear Chris Brown use it, you'll hear John use it sometimes. We can think of like P here as T pulled back. Eugenia Cheng says this as well, pulled back over S. It's like we're pulling T back over S, and we're getting like a version of T that's accounted for how S maps things, okay? So we sort of pulled T back in a way that accounts for S, okay? You can also think about this. I mean, it's symmetric, right? You can also think it as like S pulled back along here, pulled back over T. Okay. This is like a version of S that takes into account how T has mapped things. So just be aware that that's a common intuition that comes up, and people talk about pulling a morphism back. We'll see where this has real neat properties when we talk about the case of monomorphisms for set. Let's talk about monomorphisms more generally. So one of the beautiful things about pullbacks is that pullback of a monomorphism, there I am using that language, is a monomorphism. So if T is a monomorphism, if like B is a sub-object of T, of C rather, imagine like we're in set and B is a subset of C, then V will be a subset of A. If B is a sub-object of C more generally, so maybe we're dealing with causal loop diagrams. This is one causal loop diagram. This is another. This one is a sub piece of this one. It's just embedded in this one, right? Familiar notion. This is like a piece of this causal loop diagram. If we pull it back, this V, the pullback, so to speak, of A and B will be a sub piece of A, of this diagram. So here I'm talking about these being causal loop diagrams, these being homomorphisms between causal loop diagrams. Yeah. So this is sort of a sub-object of this causal loop diagram. It's a sub-piece. This is a homomorphism that just embeds it. This will be a homomorphism that just embeds this in A. Sort of get like B is to A, kind of like how B is to C or something like that. But take into account this mapping of how sort of A is mapped into C. And that's a useful notion. Notice that it occurs the other way too. If you have monomorphism here, you have monomorphism here. Now, I'm going to show you something that's just like incredibly awesome if we can get to it at the end of the session with this being sets. And it combines at once pullbacks and pushouts in a single diagram. And it's incredibly awesome. But it involves these diagrams. And needless to say, if you could have monomorphisms on all four sides, right? But if you have one here, you automatically have one here. If you have one here, you automatically have it here. Okay. Here there's this notion of like a deep notion of structure of like this is how A relates to C is kind of how V relates to B, but it's taking into account this sort of mapping here. Okay. And we'll sometimes use notation. I'm going to introduce this notation. You'll see an example in set. I know this is kind of abstract. We're going to see this with set in just a minute. I'm going to use this notation there. So this is like the version of T that took into account, that kind of takes into account how S maps A. It's kind of like T translated back into A. That's why it's S to the -1, S inverse. It's like we've taken how T operates, how it embeds something inside C, and we're translating it into how V, takes it into it relates to A. So it's kind of T mapped back to operate between these two. Okay. And so we might call this like S to the S inverse of A. It's like as mapped through this, something along those lines. Okay. Okay. So this will be something for you to think about. Yeah, I realized I haven't been emphasizing a key a key point, and I want to emphasize it for the general case, and this is actually really important what I'm going to say. This pullback object, V, everything what I said is true, but the pullback here is like the product of the categorical product of A and B. You've seen that before, right? Categorical product would be like we don't even have these morphisms, right? Mm-hmm. Like we don't even have these, right? Mm-hmm. But it's like these, but it's what we're actually taking is a more picky product. We're only considering product of A and B when they map to the same C. Okay. So you see where I'm going. So the product, if this is the terminal object, then these morphisms don't add any information, right? Because everything maps to the terminal object, right? Everything maps to the same object. Like this to terminal is, well, it's just a unique morphism. Everything maps to terminal. Everything maps to terminal. So if this is terminal, V is just the what? Product. Because there's no added information here. Like everything maps to the terminal object. Everything maps to the terminal object. But in general, if this is not terminal, V is like a subset, a sub-object of the product such that A and B map to the same C. That's the notion, and we'll see that with sets in just a minute. Okay, so here we actually have exactly this product. And that's why I'm saying we can omit those because, hey, look, there's always a morphism from B to the terminal object. There's always a morphism. We don't even have to draw it. It's always there. I mean, if we have a terminal object, it's always there. So, yeah, this is just A times B. Or another way to think about it is it's the categorical product of the A's and B's such that they map to the same thing here, while everything maps to the same thing. So it's just the product of A and B. Are we good with this idea? I mean, I know I sort of sprung that on you late, like that these have to map, but that's the essential thing here. Like this is like the product of A and B such that these the A's and B's such that the A and B map down to the same C. Okay. Okay. So let's talk about set, and maybe we can ground this in a particular intuition in our categories. I think you'll find this so familiar at some level, so sensible. Let's consider it for set, where capital A, B, and C here are sets. And what are the morphisms in set? They are functions. These are functions between these sets. Are we comfortable with that idea? Or functions between sets. Okay. So this is going to be pairs of A and B such that they're compatible in a certain sense. And that in the specific sense, that S of A is equal to T of B. So in other words, do you remember with product? Remember when we had product? Sorry, remember when we had product? We had all pair for set. We had all pairs of A and B. Right? When we had the product of A and B, it was all pairs of A and B. For every A, we'd have all B's, right? Or for every B, we'd have all A's, right? It wasn't choosy. It wasn't picky. It wasn't a connoisseur of which A and B are compatible. It just had all of them. All pairs. Remember that? Do you remember that? You're comfortable with that? So here, we're going to have a picky version of that, a more choosy, I prefer to say a connoisseur. It's going to be the pairs of A and B such that they map to the same C. So they have to be, so it might be pairs of people who are from the same province. If you had product of pairs of people if you had here people in Canada, the product would be all pairs of people in Canada with some people listed twice, right? Nathan. Okay. Here, these might be maybe T assigns for each person their province, maybe S assigns for each person their province, and in which case these would be pairs of people from the same province. Or maybe B is, and I'm using A and B the same here just for, maybe this is people in Canada, and this is their age. T and S are both mapping them to their age. And that would be integer age, say. And this would be pairs of people of the same age. Are we okay with that? Or maybe let's think about this. A is people in Canada. B is dogs in Canada. And C is maybe it's people in Canada with a home. This is terrible. It's terrible. People in Canada with a home, dogs in Canada that have a home, and C is the home where they live in. And this would be pairs of people and dogs who live in the same home. Are we okay with that? That idea? I would say, C could be, this could be all people, this could be all dogs, and then C could be homes plus one, where the one represents they don't have a home. And this would be co-product plus sort of homes plus one, and the one, and so then it would include people who don't have a home and dogs that don't have a home, all pairs of them picked up, which is a terrible thing that we even have to talk about. It's not right. Let's suppose A is people at the university, professors at the university. C is the main program they're associated with, the main academic program, say computer science, math, or statistics, or what have you. These would be pairs of students and professors associated with the same program. Will be the pullback. Are we okay with that? Does that make sense to you? As a sensible notion? Like we want compatible, and that compatibility is taken into account with this mapping, and S and T. If A and B are the same, then commonly we think of these as being the same morphism. But if this is professors and this is students, maybe they have different mapping down, but they're mapping to the same set of possibilities of C. So these are pairs in set. This has this very familiar notion of compatible pairs, and we talk about this being pairs of A and B fibered over C, or pull back over C, meaning we give in this notation that they have to have the same C. They have to map to the same C. Does that make sense? And we think of these as kind of indicating the fiber. And we'll talk about fibers sometime, but this is like a fiber, so that we have this mapping down from this. It's kind of here B over C, or A over C. Okay. Right. And I'll note the universal property holds. This is a function. This is a function. This is a function. This is some other cone that has inessential information. Maybe it sticks also the person's favorite color, and we can project it down to get just the product of people and dogs or what have you. Okay, this is from Eugenia Chang. I don't know why I don't have the. Gosh, this is from Eugenia. That's terrible. From Yi Chang, Joy of Abstraction. always be sure to make sure you indicate sources. Yeah. So here, what would the pullback of this be? Or the pullback of this diagram be? What do you think? By the way, notice of the same color. Yeah. Yeah. So here, by the way, we're with set, we're normally assuming these are the projection functors. So like this is, we just project down to A with set. We just project down to B. My understanding was that from talking with category theorists is that these, for at least for set, are commonly assumed to be the projection functors. So the fact that they aren't even shown, this is going to be some, well, it's going to be a set, right? And this is going to be the shirts from that set. This is going to be the pants from the set. It's not a monomorphism. That's right. That's right. You're absolutely right. And I shouldn't have drawn this in general as a monomorphism. Yeah. No, you're absolutely right. This is not in general a monomorphism. That is an excellent point, and I don't know why that's there. And I am going to out it right now. I'm going to elide it.
I remember you did this in that book.
Yes.
For
yes.
example of a pullback.
Yes.
You didn't use monomorphism. Yeah.
Yeah.
Makes sense.
Yeah. This in general, it's going to be this. It's not. It doesn't have a monomorphism in general. That's exactly right. And in fact,
but the reason you put the monomorphism is why you put monomorphism?
Because I was lazy and sloppy, and I didn't eliminate the I didn't eliminate it from. I copied the diagram, and I should have. I should have. I mean, there's monomorphisms are an important case, and we'll get to that in just a minute. And I think I was set on illustrating that. But in general, if I'm to illustrate this for set, these in general are not monomorphisms. These in general. The monomorphism case is a beautiful case. It's a gorgeous case, and we're going to get to that in just a moment. But in general, these will not be monomorphisms. Yeah. Thank you. That's awesome. I will copy. I'm going to hide this for now, but I'll copy that for later because we're going to use it in just a minute. The monomorphism case. Here, they're non-monomorphism, and this is matching pairs of shorts, right? Matching pairs of shirts and pants. Thank you for capturing that. That's awesome. So does this make sense? These are, to be clear, this is pants and shirts of the same color. That are of the same color, right? We good? Okay. Oh, you tell me. Okay. Multiples of 2, multiples of 5. And here we're projecting down to, this is a this is a monomorphism here of n, right? So maybe here I should use this. I can unhide it because this case actually does describe it. This is a subset of that, right? This is a subset of this. What is this here? So these are all pairs of, technically it's all pairs of multiples of 5 and multiples of 10 that correspond to the same natural number. So these are multiples of 10. Technically it's pairs of these and these that are compatible in this in the sense that they're at once multiples of 2 via this mapping and map down to the same number as this one maps down to. So I think technically it would be pairs of the same number in itself, which are multiples of 10, the multiples of 10. But it's shown here because this is completely isomorphic to that. Like, it's the same information. It's just whether you list it twice or once, it's the same information. This is the essential set. Are we okay with this one? Okay, this is the case where they're mnemonic. Yeah. Okay. This is the case where they're mnemonic, indeed. Let's talk about this. This is from Richard Southwell. He has this wonderful discussion of pullbacks, which is terrific. Okay, so I'm going to need to orient you with this. Okay, so our set A and set B, we're taking the pullback of A and B over C. Remember that it's kind of like a product of A and B, but it's more picky product where these things have to be compatible. But here we have the very special case that B is a subset. These are sets here. And B is a subset of C. Are we okay with that? And what I'm telling you is that the pullback here leads the pullback object, as it were, to be a subset of A. I mentioned that earlier, but I just want to emphasize what it's like. And this may be a little bit confusing because of artistic license taken by both Richard Southwell and I. So I'll walk you through it. Okay, first of all, here's C. We okay? And here's A over here. So we're going to take the pullback of B and A. Here's A. Here's actually B. This is B, the set B. And why am I drawing it this way? Because it's inside of C. It's a subset of C. B is a subset of C. Now, if that troubles you, you can imagine B is another set that has a mapping into C that's one-to-one. Like it's just injective mapping in. But this is a subset of C, is how we think of it functionally. B is a subset of C, so I'm drawing it as a subset of C. Again, I could draw that separate, and I could have one-to-one mapping into these in C, and that would be true, but kind of it's nice to think of this diagrammatically as here. This is a set C, broader set. B is some subset of it. And what I'm telling you is that the pullback of B and this set A is a subset of A. This one here. This is the pullback of A and B fibered over C, okay? Where B is, in other words, a subset of C. What happens? This may look kind of confusing. Let's think about this. Well, first of all, I think you'd all agree there's a mapping S. These are sets. We're drawing it for set. So this is a function from A to C. And that's what I've drawn in these. Do you see these green lines? I've drawn that. Now, the magenta lines will also be of that, but they're a special one. I'll show it to you in just a moment. So all these lines going across here are maps from A to C. Are we comfortable with that? Maps from A to C. We good? No objections? Okay. Okay, so these are maps from A to C. And what the pullback is doing here, the pullback is a really powerful operation. What is it doing? Well, it's taking this relationship from B to C and pulling it back over S, pulling it back here, translating it to set A, and finding a kind of comparable subobject of A that is kind of like B is within C, this will be within A in the same way. It's pulling back T. T is this inclusion function that sort of relates B to C. If we had drawn B separately, we could have drawn it in here explicitly with T. And this is kind of T of B. It refers to this being a subset of C. And what we're doing is we're taking that, like B is to C, as like the pullback of A and B of fibered by C is to A. So the pullback operation is like taking this relationship of B within C, pulling it back to operate with A, and it finds that the image of B here is a subset, in the pullback here, is a subset of A. And what subset is it? Well, it's a subset of A that maps via S to B. So Q here, it is in S. Yeah, it's a sub. This is a subset of A. This is a subset of C. And so Q is completely compatible with S. It just does what S does, but it does it for this subset of A. This subset right here. So this is like to A. This one is like to A as this one is to C, as translated back by this mapping between them S. And we just call S for the subset Q. This is S for Q. It's the version of S that applies to this subset, to translate it to there. And so we can think of it as S pulled back over T is what Q is. S is pulled back over T, and it applies to this subset that is sort of the comparable subset of A. So here, the pullback of this, given this mapping, pullback of this is like the pre-image of B, right? It's like the things that map into B via S. There's all these things S maps over to C. A subset of them map to have their image in B. And those ones, this pullback object set, pullback set, is the preimage of those. It's the things that map over into B via S. So that's pretty cool in my view. That the pullback here is like finding the analog to B within A. It's finding the analog to B, just as B is to C, we find the pullback is to A, as taking into account this mapping between them. So you can see why this notion of like pulling S back over T, or equally pulling T back over S, this inclusion one for S, why that notion kind of makes sense here. And you can kind of see graphically just how the pullback is operating. It's finding this analog sort of to this mapping as it applies to A, taking into account this mapping S. Are we okay with this? Now notice that I drew S as injective here. Like in general, S needn't be injective, right? Like in general, there may be multiple of these ones that are mapped to the same. In fact, there could be multiple of these that are mapped to the same one here. And that's fine. That's fine. No problem. I just drew it sort of didactically to avoid worrying about that. But in general, there might be several of these that are mapped to a given object here, and that's fine. That's fine. But the point is Q it's completely compatible with S. It's just S applied to this little subset. We good with this? All right, so this is this very interesting case where like this is a monomorphism. And this has its analogs in where we're not dealing with sets. Maybe these are objects or causal loop diagrams, morphisms or homomorphisms, and we get B as a sub-object of A. We pull back over this homomorphism that switches things down or maps this and that, and we take that into account and we get a comparable sub-object of A, a comparable subset of A. Take into account how A maps things down into C. It may map multiple things down, and so it's delineating this kind of sub-object of A that is like what B is, but takes into account this mappings mapping down that S does or something like that.
It's like assume A and C are knowledge graphs
Yeah,
or different disease or
yeah,
phenomenon.
that's right.
Actually, yeah, pullback is to filter the local information in A related to C.
That's really
Common
nice.
information.
That's really nice. Okay, I will need to learn from you more on that. That's really, really interesting. Okay, so knowledge graphs. Here you go. For ontology logs. So EJ is referring to the fact that David Spivak's book, Category Theory for the Sciences, drawing on his work with Kent from over a decade ago on ontologies, very powerful work, very tied with CSATs, because can use CSATs to capture ontologies. Richard Southwell is using this here in this nice, beautiful video on understanding pullbacks. So C is some amount of fuel. Here, there's some amount of diesel that is an amount of fuel. So this is kind of a morphism here. This is this. Here we have a car has an amount of fuel. And you take the pullback over this, and you have a car paired with an amount of fuel. That's the amount of diesel. That's the amount of fuel that the car has. So it's taking into account like, okay, you have an amount of diesel, you have a car, but they're compatible, right? Like it's not a car in any amount of diesel. If this were product, if we didn't consider how much fuel the car had, it would be a product, right? All cars with all amounts of diesel. Here it's a car with an amount of diesel that it has. And that's what this is. This is ontologies. And these are relations such that this commutes. So, all pullbacks groups has to communicate. Ontology is a really nice way of capturing things, and I will say, as UJ knows, ontology is one of these things that are being used with sheaves now, which is fun. Okay, this is like god awful beautiful. This is like incredibly beautiful. In fact, my wife knitted this into her category theory scarf that she made for me, which has impressed category theorists throughout the world. Okay, so here's here we have set. A is a set, B is a set, and these two are sets. B is a subset of A union B. Do you agree with that? A is a subset of A union B. Do you agree with that? So if we take the pullback of A and B here, if we pull back T over S, or we pull back S over T, we get the intersection. This is the intersection of A and B. This is monomorphic. This is a subset of B. This is a subset of A. This is the union of them. So B has to map to the same thing in the union that A maps to. What's the thing that allows that to happen? To have compatible A's and B's in the sense that they map to the same thing in the union? Well, it's precisely their intersection. That's the subset of A and of B that maps to the same thing in the union, the same element in the union. Is that awesome or what? My wife thought it was pretty awesome. So she built it into the scarf. Okay. I have a few others, but this is my favorite by far. This is like by far, this is the most impressive scarf I've ever seen because it has adjunctions in it and it has commuting squares. It has it may even no, it doesn't have equalizers or co-equalizers, but it is just like god awful awesome. It's just incredible. Okay. So I would just say in algebraic stock flow, as several people here know, we use pullbacks. So if we have some model and we have some stratum over the model, maybe by age, we have a stratified version of the model where we age stratify things that map down to the same thing in the type model. So this is, if we were totally independent, we didn't have to worry about this. We might have, maybe it'll be easiest to think of this as like age and this is like sex or something like that. We might have the product of all ages and all sexes, but potentially there might be things like this could be age and this could be employment category, but they have to be age and employment categories only exist for kids of, for people of a certain age, not for kids. And so there's some dependency between them. And in general, this could be, for example, an aggregate model, and we wish to stratify it by age, and we can have a stratified version, but there may be some things we don't want to stratify for. And so we map them down to a thing for which we
why the
yeah.
factor example in stufflow.gl, I'm always confused because some code block saying tabbed model, tabbed, as assuming which is S tab here. What's the meaning of S tab exactly?
S tab.
Yeah,
The type.
Type. Sorry, tab.
Yeah.
Type.
Yeah. Okay, so here's the deal. I won't go into this in detail. We can go into it more in the office hours, but this is an awkward thing, and we've talked actually with John about eliminating the need, but right now it's an issue. So imagine that this has aging. Okay. Imagine this has aging. So we want to capture age, different ages. If we want to capture different ages, we also have to capture progression among ages, right? And maybe this involves location where people live. So Regina, Saskatoon, and other. And you're going to have some movement between them. Okay. Remember here, if this is a stock flow diagram, and this is a stock flow diagram, the question is, what are the morphisms? Morphisms are homomorphisms of stock flow diagrams. And S-type allows you to say what the aging morphism maps to. And you could have in this diagram certain things that map to that, that you want age to apply to, for example. So S-type in general will have morphisms representing this, morphisms representing this. There may be certain things that you don't want to stratify by, for example. Maybe, for example, you want to stratify the people stocks, but you don't want to stratify the stocks of cumulative infections that have been built up. Or you don't want to stratify the stocks of mosquitoes by age. You don't, and so in type, you might have certain stocks that you want to apply the age to, and certain stocks you don't want to apply the age to, for example. And so you would distinguish that by mapping, like here, down to things which should be stratified, and mapping others to things which shouldn't be stratified. This would do the same thing. Some things, it would indicate in the aggregate model which things should be stratified and which things should not. And this would take the pullback, and that would allow us to basically stratify by some things that and not stratify by other things. Yeah, I'd have to spell that out more. I've got some fuzziness in my head, but the type allows you to distinguish how you want to handle certain things and where things like what things here correspond to what things here. Like that you want to have aging here that might correspond, and you sort of mark it here. There needs to be a homomorphism down to this that allows you to do something with the aging flows. But meanwhile, there's other things you need to map down to say, I want to consider something here to apply to something up here. Anyway, we can figure this out. Okay, so this is push outs.